will award one of our more senior students the opportunity to go through their talk with all of you to be given an award, which we'll talk about in a moment, from Leidos, our sponsor, and then to have a great round of Q&A and discussion with everyone in attendance. We really want this to be a great example of the quality of work, the breadth of work that happens in our lab, and we want to celebrate that with all of you. So that's what we're here today to do. In a moment, I'm going to kick it off to Jack Stankovic, our director of the Link Lab, to talk a little bit about the award. Then we'll go to Leidos, our sponsor. They've been partners of the lab for a good while now, since our inception. And they're the sponsors for this award. And then we'll go to Professor Bezo, the faculty member for our awardee, Esen. A couple of things just to note is, number one, we are being recorded. So the idea for today is to be able to showcase this talk publicly. So we want you to know that you're going to have the opportunity to ask questions at the end. You have two options there. One is to go into the Q&A section and just write out your question, and we'll read those out at the end. Or you can raise your hand. You can use the little indicator in Zoom to virtually raise your hand, and we'll alternate questions between the written Q&A and the hand raisers at the end. Any other questions, you can come to the chat section. Both Jennifer and I will be in there helping folks out. But otherwise, let's go and get started. So I'd like to introduce Dr. Jack Stankovic. He's our director of the Link Lab and a professor out of computer science who could be talking about the Link Lab and this award that Esen has gotten. Thank you.
All right, thank you, Travis. So I thought I would just say a few words about the award and how it fits into the kind of bigger picture of, let me see if I'm supposed to have my video on. All right, so I thought I would say a few words about the award, how it fits into the bigger picture of what we're trying to do. And, you know, our goals are world-class research in cyber-physical systems, strong research, education, and professional development. So we have all of those, and we really want to support our students, and we want to promote our scholarship. And so this basically does all of that. And, you know, the idea is that we can see a highlight of some excellent research that's happening in the lab, and the student gets to practice a talk, maybe use that for their job hunting. They get feedback on the talk. They important to put this award on their vita, so it helps their job search as well. And it also showcases the excellence of what they're doing. The award was done by having a nomination period where we got quite a few nominations, and we targeting senior students, those who are about to leave the Link Lab and go out to the real world out there. And then faculty voted, and they voted on 3 people. And then the overall winner is Esen. And it was very competitive. We have such really great students. So we have no shortage of super work being done by super students. And I thought also, I want to point out that we kind of created other mechanisms as well. So, for example, we still give annual awards for research and service, which we will continue to do. We started that last year. We're putting into place these flash talks, which are also able to provide more input about what's really going on here. And then, we have these weekly news about papers, awards, grants, and so on, good things that are happening. So please definitely send those kinds of activities to Travis. He sent a link around. And so, I think that's another very major way of getting people to know what's going on, especially when we're not in the lab itself. So that's all I really wanted to say. I really want to get as soon as possible to Esen's talk. I'm looking forward to it. And I would like to introduce, our Leidos representatives. I mean, Leidos has been our industrial partner from day one. They're a great supporter of our lab, and we truly appreciate their support. And we have two representatives. JP Skaduda is an engineering lead, and also Ellen Korkovelos, who is a product owner for C2 Unmanned. And so I'll just turn it over to them.
Thank you very much. Good afternoon, everyone. I'm JP Scaduto, an engineering lead here at Leidos, and I'm here with Ellen, one of our product owners out of our Charlottesville software factory. I just want to start off by thanking all of the students, faculty, and staff who help organize all these great events. I know a lot of hard work goes into them, and we really do appreciate everything you've done to make it possible. At Leidos, we focus on making the world safer, healthier, and more efficient through technology spanning across domains in defense, intelligence, civil, and health. Our partnerships with universities and research labs like the UVA Link Lab have proven to be invaluable to our mission of improving our communities. Leidos has been a Link Lab industry partner for a number of years, and through this time, we've had the opportunity to collaborate with the faculty on initiatives such as the Crozet Tunnel modeling, working with students on capstone projects, sponsoring research, participating on panels in autonomy and smart systems, and working together to foster a tighter community in UVA, in Charlottesville, and beyond. We are frequently reminded of the importance of the research being done in the Link Lab and the applications it has in the real world. As autonomous systems become more commonplace and start to emerge in everyday life, we search to know more about the trust and reliability in the decisions these systems make as they grow into critical parts of our society, from healthcare to flight systems and on. The Link Lab, being a center of expertise, has demonstrated several accomplishments that continue to drive our commitment and excite us for what's to come next. The collaboration and relationship that we continue to build between industry and academia is vital for making innovation in technology, building the future workforce, and building a better world. The student seminar recognizes the hard work, determination, and talent demonstrated by the students in the Link Lab achieving excellence in research. We're honored to be here today to celebrate this with you. With that, Travis, we'll hand it back over to you.
Thank you, JP. So along with this award comes a certificate and actually a cash award that is part of that sponsorship and the support from Leidos as a recognition from the lab to Esen. Normally we would do this in person and hand a piece of paper, a certificate and a check over, but that'll be virtual. So Esen, be on the lookout for that. And again, thank you. So now I want to hand it over to Professor Nicola Bezzo. This is Esen's advisor and research lead, and for him to give an introduction about Esen and about her work and about the project that we're highlighting today. So, Professor Bezzo?
Sure. Thanks, Travis. Thanks, everybody, actually. So yeah, let me actually, I cannot start my video for some reason. Tell me, okay, perfect, okay, awesome. Okay, hi, everybody. So yeah, it is really with great pleasure that I introduce Esen. I'm very happy that she's the recipient of this award, and actually even more that she's my student, to be honest with you. Esen is a brilliant student. She joined my group about 4.5 years ago, and her research has been growing exponentially since she started working with me. She's working on a DARPA Sure Autonomy program. Her work is featured every year in top-tier robotics conferences that include ICRA and IROS, that are two of the major robotics conferences, and also in major journals and magazines, including like a recent special issues in the prestigious Robotics and Automation magazine. Esen work covers control, motion planning, machine learning, with one big intent, that is to improve autonomous robotic systems and make them more resilient and safe against the disturbances, failures, and in general unknown that can happen during runtime. So I'm not going to spoil too much presentations. So without further ado, please join me again in congratulating Esen. She's been doing a really great job. She will be missed when she leaves the lab, and I hope you will enjoy her presentation. Thanks.
Thanks, Nicola, for the introduction, and thanks everyone for joining this talk. I'm really happy, and I'm really happy to like present my work to all of you, and I'm really happy to have this award. So thank you for considering me for that. And I believe I'm able to share my screen, so if you can let me know.
We can see it. Okay,
awesome, great. So today I'm going to be talking about my research, as Professor Bezzo mentioned. It's on safe autonomous robotic operations, mostly on runtime monitoring and predictive planning aspects of it. Thanks to the recent technological advancements, autonomous robotic systems are started to be widely used for different applications, including package delivery, medicine delivery, agricultural purposes, surveillance purposes, inspection, hobbies like photography, and household applications. According to FAA, there are more than 1.5 million registered drones in the United States. This means that these vehicles are widely used in our daily life. And that's why I'm also more focusing on unmanned aerial vehicles in my research. So one of the most common used aerial vehicles are quadrotors, which have 4 motors, create agile and fast motion. So I want to introduce these vehicles in more detail now. These vehicles are able to carry different sensors, such as LiDARs and stereo cameras or regular monocular cameras, which allow them to understand and recognize what's happening in their environment, such as detecting obstacles and avoiding them. Additionally, they also have computation on board, which allows them to be completely autonomous. These systems have complex dynamics, and that makes them very agile and fast. And thanks to these advantages, these vehicles are widely used in our real world. However, when these systems are used in the real world, they face numerous different uncertainties. One of the main uncertainties that they face is the external disturbances, such as heavy winds that happens in the outside. And they also can be tasked to carry different unknown payloads. Also, they're subject to signal occlusions, especially when they're moving in between tall buildings in cities or in the forested areas around trees. Also, they are subject to model changes over time, which may happen because of the actuator failures. So there may be sudden, or there might be gradual changes due to the system's aging. And while they are subject to these changes, guaranteeing their safety is very critical. And that requires to take these uncertainties into consideration while planning their motions. For example, in this video, I'm showing a case where when we recorded in our lab, and this quadrotor is trying to actually follow a safe trajectory in between these 2 obstacles. However, we are blowing a heavy wind by these 2 fans, and this pushing the quadrotor close to these obstacles and actually causes it to collide with these obstacles, even though the original trajectory was safe, because we didn't consider the disturbances while designing these trajectories. So these kind of situations are not desirable because they're not safe for the vehicle itself, and they're not safe for the environment either. So to consider these uncertainties can be really computationally expensive. However, these vehicles are small and they don't have unlimited computation on board. So given all these challenges, my research objectives include to efficiently and accurately predict the future states of the systems under various disturbances and uncertainties. For example, in this figure, I'm showing these possible future states of the system by these orange and blue regions. So our purpose is to predict these regions accurately and then use these regions to minimize computation and guarantee safety and liveness. And here by safety, I mean that there's not going to be any collision with the obstacles. And by liveness, I mean that these systems are going to be able to track their trajectories closely and also able to reach their goal. And as I mentioned before, there are also model changes that might happen during the runtime. So another objective of my research is to learn these model changes and its effect and the effects of these changes on the system's behavior and use these predictions to prevent unsafe situations. So during my talk today, I will first talk about our efforts to predict the future states of these systems and how we use them to minimize computation. And then I'm going to talk about our research on how to create these reachable sets fast at runtime and also bypass them completely at runtime. Then I'm going to be talking about the techniques that we developed to deal with unbounded disturbance problems and also runtime model change problems. So as I mentioned before, we would like to predict the future states of the system under disturbances and uncertainties accurately. And we want to use these regions to minimize the computation related to the periodic sensor monitoring. Traditionally, the autonomous systems monitor their sensors to detect the obstacles or detect their own positions periodically. And however, this is not always necessary. For example, when these systems are flying in an open area like a desert, there are no obstacles around them. And they don't need to check their sensors all the time to be safe, because even if they don't check their sensors, they can be safe in these open areas. And monitoring these sensors are computationally expensive. So we are dealing with the problem of scheduling the next sensor monitoring time while being safe and liveness. So for this purpose, we are using the reachable sets. Reachable sets are a set of all the states that the system can reach over a certain time duration. So for example, here we are showing this tube, the orange tube, which is a reachable tube, which shows where the system is going to reach over time under various disturbances and uncertainties. Then we can use these reachable tubes to understand when the collision with an obstacle may occur in the environment. So this is the first time these reachable tubes are colliding with any of the obstacles. And we can also check what is the earliest time that the system can leave the sensor field of view that is already observed. And this is the first time these reachable sets are not contained by the sensor field of view. And we are scheduling when to check the sensors again, according to the first time, one of these times, which one is the earliest. And before this time, the system is guaranteed to be safe. So here's one example of our quadrotors, which is moving according to the approach that I just mentioned. So the system is using its LiDAR sensor to detect these two obstacles according to the times created by our approach. So by only checking the sensor at the times, which are shown by these quadrotor icons on the top left corner, the system is able to avoid all the obstacles and complete its trajectory. By using our approach, we are able to decrease the CPU utilization from 9% to 2.7%. So as I showed in the previous case, these traditional reachability analysis techniques are very powerful and useful to guarantee safety. However, they require the full knowledge of the system, and they also can be computationally expensive if the system is trying to make predictions for a long amount of time. Additionally, normally the systems are periodically measuring their sensors to understand where they are, their position sensors. However, in sensor-denied environments, such as like in a city when it's moving in between tall buildings, the system may not be always monitor its position. So in order to deal with these problems, we are proposing two approaches. The first one is the Gaussian process-based fast reachability, that we are using Gaussian process regression technique to construct these reachable sets fast at runtime. And then second, while the system is moving under sensor-denied environments by only having intermittent position measurements, by using self-event-triggered scheduling, planning, and recovery approach, we are guaranteeing that the system is going to be safe. So this approach consists of two stages, and during the offline stage, we collect the training data by creating different motion primitives for the system. And these motion primitives are executed under a rich set of disturbances. After collecting this data, we use GPU regression technique to estimate the maximum deviation for a different trajectory. Then this maximum deviation estimation is used to construct these reachable sets fast at runtime. And here is one of the simulations that I ran using this technique. So the system is not able to observe its position all the time. It is only getting position information intermittently at random times. So we are using our technique to create these reachable tubes shown on the right, fast at runtime. And when these reachable tubes are colliding with obstacles, we are making the system to observe its position by changing its altitude. So by using this technique, the system was able to complete its course without needing to monitor its position information all the time, and still was safe and didn't collide with any of these obstacles. Similarly, we trained our quadrotor by running different motion primitives on our quadrotor under wind disturbance created by Esen, and then trained the GP regression model. Then we use this GP regression model to construct the reachable sets when the system is following a different trajectory in between two different obstacles. And there's still a fan blowing wind, which is creating disturbance in this case, and the system is getting position measurements intermittently. And by using our technique, similar to the simulations, the system was able to complete its trajectory safely, and the reachable tubes that we created contained the actual state of the robot. So reachable sets are useful, and they are used to understand, to guarantee the safety of the system and understand if the system is going to be safe or unsafe. However, when this is the only reason that they are used, when they're only used to check if a trajectory is going to be safe or unsafe, this computation can be actually bypassed completely at runtime. To do that, we propose to use neural networks to understand if the trajectory is going to be safe or unsafe under disturbances. And we verified these neural networks again during the offline stage, so that we can use the decisions of the neural networks to plan safe trajectories at runtime. So during the offline stage, we use the traditional reachability analysis techniques, which can be computationally expensive, to label the trajectories as sampling training trajectories as safe or unsafe. If the reachable sets are not colliding with any of the obstacles, the trajectory is labeled as safe. Otherwise, it is labeled as unsafe. And then we use these training labels to train a neural network to make a decision about a new trajectory, which weren't in the training set. However, neural networks may be subject to errors. They may not always create accurate decisions. However, as this is a safety-critical system, we would like to verify that the system will never reach unsafe states when the neural network output was safe. To do this, we use a verification tool called VeriSig, where the neural networks were converted to hybrid systems and composed with the planner, planned, and the controller hybrid systems. And by using traditional hybrid system reachability tools, the neural network was verified that it was never going to output safe decisions if the system can be unsafe. However, if the training data isn't enough, or if the training wasn't done properly, the verification may fail. So for example, in the case shown in this left figure, there are some regions shown by these yellow rectangles. And in these regions, the verification couldn't have any conclusion if the neural network is safe or unsafe. So it was unknown. So since there are unknown regions, this neural network was not verified. However, we propose a technique to use the output of this verification to retrain the neural network by adding artificial unsafe points in these unknown areas and inflate the unsafe region in the neural network. Then by inflating these unsafe regions, we can now verify the neural network to be safe and use at runtime. So here we are showing an example, a simulation example where the neural network decisions were used. This is a bigger environment than the training environment. However, these training environments were composed according to positions of the obstacles, so that we can use neural network decisions. So we are using the neural network decisions to find a safe intermittent goal. First, the system picks a goal which is closest to its global goal. And then if this is deemed to be unsafe according to neural network decision, we query new intermediate goal positions until we get a safe one. So after the neural network found a safe goal position, the system moves to that goal position and guaranteed to not to collide with the obstacles even under disturbances. Similarly, we did experiments using the same approach where we trained a neural network based on our training trajectories labeled as safe or unsafe. And then we use this neural network decisions to find intermediate goal positions in a bigger environment where the system is tasked to go in between these three obstacles. And the neural network decisions are used to find these safe goal positions, and the system was able to complete its trajectory without colliding with any of them. So far, all the topics that I mentioned were considering different disturbances. However, all of these disturbances were assumed to be bounded by the training at runtime. However, in the real-world scenarios, this may not be always true. In some of the cases, the runtime conditions can be outside of the training bounds, and this may cause failures. For example, let's look at this quadrotor, which is tasked to carry a payload at runtime. So during training, this quadrotor can be trained to carry up to a certain amount of payload. If at runtime it is tasked to carry a larger payload, then it may cause it to lose altitude and hit an obstacle or hit the ground. So we would like to prevent these situations, and our approach includes to estimate this type of disturbances which are happening at runtime and their effects on the quadrotor's behavior using GP regression. Then we would like to use these estimations to prevent failures, and we would also like to use the knowledge which are observed during the runtime to improve decision making. So this approach is consisting of, again, two stages, offline and online stage. And during the offline stage, the system is tasked to follow different trajectories by carrying different payloads. And then we use the observed data to train GP regression models to first estimate the payload disturbance and then estimate the deviation of the deviation caused by this payload estimation. So in these figures on the left, I'm showing two cases where the system is tasked to follow a trajectory with two different speeds. This can be observed with the increased speed and increased payload. The system deviates in Z direction more. So our GP regression model maps the speed and payload to the deviation, to the Z deviation. And then at runtime, during the online stage, when the system is tasked to carry a different payload, this payload is estimated, and then we use this GP model to understand what's the speed that the system needs to go with to avoid the obstacles in the environment. So after this decision is made, since the training can be limited and these GP regression decisions may not be accurate all the time. So if that happens, we have an online recovery approach, which takes the system to a safe position, and then there we find a new speed by using an SVM decision model. So if the first speed was unsafe, then this is labeled as unsafe, and SVM is retrained to find a safe speed for the system to go in the after the recovery. So here I'm showing the simulation results using this technique. And in the first round, the system is tasked to carry a payload, which is larger than the training payload. And then using the GP deviation model, the system finds a speed which keeps it safe and makes it finish its trajectory without colliding with any of the obstacles, this window-shaped obstacles. In the third round, the system is now tasked to carry a larger payload and makes a decision using the GP model. However, this decision, the speed that it picked was too high, and it made the system to lose Z altitude very fastly. So when this happened, we triggered the recovery action, and then the system went up to hovering position, and then replanned a new speed, which is now slower. And in the last round, the system now is tasked to carry the same payload as in the third round. However, now, thanks to all the information that the system collected during the runtime process, it is able to pick a speed which is slow enough for it to avoid the recovery action and finish its course without colliding with any of the obstacles or needing to perform any recovery action. So here are the experiments that we use the same approach, where the system is tasked to carry different payload disturbances than the training. And as similar to the simulations, it is trying to go between initial and final goal position when there is an obstacle in between. And the system is adapting its speed, picking slower speeds when it's carrying larger payloads as expected. So in addition to the disturbances that can happen at runtime, which can be bounded or unbounded, there are also cases where the system can be subject to unforeseen component failures and model changes. And these kind of component failures and model changes may cause the system to move under degradations, which is not desirable because that may make the system not to finish its task completely. So for example, here in this figure, I'm showing a case where the system is tasked to follow a pipe and inspect this pipe. However, and at this position, there is the system faces an actuator fault. That makes the system deviate from its desired position, desired trajectory, and go away from the pipe, which makes the system to not be able to inspect the pipe properly. So to prevent such failures, our objectives is to predict the future state of the system when it's facing a different fault, and update its reference trajectory in an adaptive way to improve its trajectory tracking performance. So our approach includes meta learning, which is a new machine learning technique, also called as learn to learn. And it uses the previous experiences on different models and then trains a meta-learned neural network. And this meta-learned neural network is easy to fine-tune with only a few data at runtime. So we are proposing to use meta-learning to predict the future states of the system. And then we also introduce a control-based technique to update this reference trajectory adaptively. So during the offline stage, we collect training data under various different actuator faults. After collecting this data, we train a meta-learning model by using this offline data, which is easy to fine-tune. So during the online stage, now the system is experiencing a new fault, which can be outside of the training set. When that happens, it collects only a few data at runtime. And then with only this few data, it is able to fine-tune its meta-learned model according to this data. After fine-tuning the model, we use this model to estimate the future state, to predict the future state of the system accordingly. Then this prediction is used to update the reference trajectory based on the deviation from the current and original trajectory. So here the idea is to trick the system, try to follow something different than its original trajectory which is in fact make the system follow its original trajectory better. And there's one problem, which is that the initial updated meta-learned model may not be always accurate if the system is performing different maneuvers and or different or initial data may not be always representative of the entire trajectory. And in order to predict if this happens or when this happens, the predictions coming from the meta-learned model is always compared with the actual position of the system. And if these predictions become off, then we trigger an online learning where more data, more recent data is used to relearn the model and fine-tune this meta-learned model even more. So here I'm showing some of the simulation results where we create, during the training, we created faults on propeller 1 and 2 of the quadrotor. And then during testing, we have a fault in the propeller 4, which is completely different than the training. So we train our meta-learned model by using these 4 different faults, and during the online stage, the system collects data initially and then updates its meta-learned model and then uses these predictions to update its reference trajectory. So we are tricking the system to follow this pink trajectory to make it follow its original trajectory better. And this red line is showing what if we didn't use our approach. So as you see, if we didn't use our approach, the system was going to collide with obstacles. So when the predictions become off, we trigger an online learning and the system use more data to re-update its meta-learned model. So here I'm showing that by using our technique, we achieved to have really small deviation from the desired trajectory. So this is the experiments that we done using the same technique, where we created a fault, an artificial fault on the quadrotor, where we added bias to one of the bias to the roll angle of the quadrotor and created different trajectories with different speeds. And after training, we use this meta-learned model to make predictions. Here I'm first showing that what would happen with a different fault if we didn't use our technique. And as you can see, the system deviates from desired trajectory. Desired trajectory is shown by the green line, and the actual position was with the blue line. So then I'm using our meta-learning-based technique to update the reference trajectory, and the system is actually following the desired trajectory much better. So in summary, my research focuses on guaranteeing safety for autonomous systems. I use reachability analysis techniques for this, and also to minimize the computation, unnecessary computation related to sensor monitoring. Our research was also having efforts to have this reachability computation fast at runtime by using machine learning techniques, and also introduced runtime monitoring and online learning techniques to improve decision-making over time. The future directions can include to use these reachability analysis techniques for the systems with model changes at runtime by leveraging the model's learning uncertainties, and also utilizing knowledge about the previous failures and nominal reachable sets. Risk analysis can also be used for the systems with failures to understand what action to take, which is the less risky action to take. And also cyber-physical system security can be improved by using reachability analysis. Most of my techniques were applied to aerial vehicles. However, they're not only working for aerial vehicles, they can be applied for other vehicles like ground or underwater autonomous systems. Thank you very much for listening and for your attention. I'm happy to answer questions if you have some.
All right, thank you, Esen. That was great.
Thanks.
So we do have a couple of questions coming into the Q&A. So now I'll just ask everyone to, like I said, either throw a question into the Q&A and I can read it out, or if you'd like to ask in person, please virtually raise your hand. We can't see you, so don't actually raise your hand. Within Zoom, virtually raise your hand, and we'll come to you. So I think first, we have a written question from Professor Furukawa, but we're actually going to live his mic as well. And he has a question about, I think it has to do with your reachability approach with low speed versus high speed vehicles and other, and then a follow-up question about fixed wings. So Professor Furukawa, if you're up, please go ahead and ask your question.
Yeah, thank you. It was a very interesting talk, and it's also my first time to hear the talk of Nicola's students, and so I really enjoyed also learning, about what Nicola is also doing, more specifically. So I have two questions. I would like to just ask in a different ways. The first is relevant to what I have already posted, but you are using a reachable set. So the reachable set is quite useful, particularly for high-speed vehicles, because the dynamic effect is going to be shown in the reachability reachable set. Whereas the drones are generally, it can also fly the low speed as well. So when you are practically using it, how did you find the effectiveness or usefulness of the technique? Let me just ask this question first before I just move on to the next question.
So most of the time, we didn't try to make the system go really with high speeds. It wasn't the purpose of my research, but more so we used reachable sets to understand where the system can reach under disturbances. So more of the effects of disturbances on the system rather than the effects of high dynamics or the fast, the speed of the vehicle. Does this answer your question?
Yes, yeah, I understood it because it's obviously useful when, for example, that you are actually just crossing the window frame and at reasonably high speed, and in such cases the forward reachable set is quite important and useful. So but I also understand that it's also very useful for disturbance. So thank you very much.
Yeah,
the second question is about the localization. I think you are using, flying in the Vicon environment, and are you assuming, there is no localization error? Because when you are also flying the drones, you also mentioned about model uncertainties. I think you're more talking about the motion model uncertainties, but we also have observation uncertainties, the model uncertainties as well. So, which basically creates the localization error of the drones. So. I know that you tried to handle it in the GP's framework, but I just wonder if you are, taking the localization, error into account.
So yeah, in my simulations, in most of them, maybe not in all of them, but I also included the measurement uncertainties, which is basically the localization uncertainty. So if you get a measurement about your state, I also added some noise, bounded noise on this measurements to consider that effect as well.
Okay.
But when we are running our experiments, yes, you were right. We were using Vicon motion capture system, which is pretty precise.
Right. Yeah. So I'm also really interested in to me, since I am not using the GP, so I'm really interested in also knowing how your technique is going to work under the localization errors. Yeah, I'm very interested in.
Yeah, we can also follow up if you want to have more details on in any of these. I'd be happy to share my papers with you or have a talk with you.
Oh, definitely.
Yeah, thanks.
Thank you very much. It was very interesting.
Thank you so much.
All right, thank you, Professor. So just so everyone knows, the way we're going to do it is I'm going to alternate between written and these live questions. So we have another written question here. Is the reachable set computed after a fixed duration? And they follow up with, is that from the expected set point on the original trajectory or a new actual measured state of the UAV?
Is this for any specific technique or that I showed, or?
It seems to be as you talk about understanding the reachable set and having the UAV understand where it is and run its calculations based on that. Are you updating new reachable sets as you do actual observations? I think somewhat related to.
Yes. So when we observe, first initially we created these reachable sets for the worst case scenario, assuming that the disturbance can be like up to certain bounds. And then, however, like if the disturbance is lower, the system will never actually reach the bound of these reachable sets. And when we get a measurement, we kind of understand that that was the case. It didn't have that much of disturbance, and update our reachable sets, decrease the size of it, and update the reachable sets itself based on the new observation that we got.
Right. Okay. Thank you very much. And then next up, we have a live question from actually Professor Jack Stankovic. So go ahead, Jack.
Yeah, hi, Esen. Yeah, I found the talk really interesting also. Thank you.
Thanks.
I'm trying to understand exactly what you mean by guaranteeing safety, though.
Mm-hmm.
And, in aircraft, like Boeing, they guarantee safety, but it's 5 nines or something like that. There's a probability of it being safe, 0.9999.
Mm-hmm.
And so I'm not clear where your guarantee is happening and whether it's probabilistic. There's an offline portion and there's an online portion, and then there could be unknown disturbances. So what is the definition of guaranteeing in your work?
So when we construct these reachable sets, we are assuming like bounded disturbances, or when we assume that, and if the actual disturbance is actually bounded by that amount of disturbance, then it's, according to the reachable set computation, the system is going to stay within these bounds of these reachable sets. And we are saying that if these reachable
with 100% probability.
Well, so of course there is a difference between the simulation and the real vehicle. So if the real vehicle model can be completely extracted fully, then yes. However, there can be also a gap between the actual model of the system and the actual vehicle. So that's also an open research that we've been thinking about how to close that gap. However, if the system's model can be extracted completely, then yes, it is going to be inside these reachable sets, if all the assumptions are held.
Okay, so just clarification, all your obstacles are static, right?
Yeah, in the talk that I showed, yes, it was. I also dealt with dynamic obstacles, but I didn't include them in this talk.
Okay, all right, thank you.
Mm-hmm.
Great, thank you. So we have another question here, a couple of questions from Winston, and I think we're going to flip them. First asking, says, what sensors or how do you detect the wind and other obstacles? When we think about these disturbances, both environmental and then, in this case, the static objects, can you talk about how the UAV, the platform, is aware of those different ones by your different sensing or awareness modalities?
So for the wind, we didn't use any sensors to detect that. We just created those winds. For the obstacles, these systems have LiDAR and cameras on board that can be used to detect the obstacles in the environment. So in some of my experiments, I use my sensors to detect them. In some of them, I use the motion capture system to detect the obstacle positions, depending on the case scenario.
Okay, so for that dynamic interference like wind, it's just situational awareness of the location of the UAV, which is in fact the sensor of the wind.
Yes.
Okay. And then he asks another question. So as he understands, you're using machine learning to do a good portion of the UAV control. Of the different techniques you talked about, what's the biggest novelty? Like, where did you see the biggest jump over current state?
So I would say using machine learning techniques to do the actually understand when the system needs to take certain actions, needs to do replanning, and needs to make sensor observations to avoid computation by creating these reachable sets. So I think combining these machine learning with the motion planning of the quadrotors is the novelty for safety purposes.
Nice.
Yeah.
Great, thank you. I don't see any hands raised. So we'll go back to another written question here, which actually also came from Professor Furukawa originally, and I don't believe he covered it in his first question, but so you do mention in future work looking to ground and underwater.
Mm-hmm.
Would this play a role in fixed wing UVA navigation?
It could be applied to fixed wing as well. I didn't use them in my experiments. I don't have that much experience. We usually just like use quadrotors in our lab, but yeah, I don't see why not. It can be applied to fixed wing UAVs as well.
Would the pathing of fixed wing versus sort of more agility of rotary change any of your kind of fundamental techniques that you can think off the top of your head?
I don't think so. As long as there can the motional, as long as the models of the fixed wing can be also fitted in my, I think that can be fitted in my techniques mostly. So I don't see like a big difference that can be done to my techniques to apply to fixed wing UAVs.
Yeah, makes sense. Okay. Well then, I don't see any other questions popping up in the written or in person. So with that, I think I just want to say thank you so much for your presentation and congratulations, Esen. We're all just extremely proud of all the work that you've done while at Link Lab. And I think adding into what Jack said in his opening, I think for a lot of us, even more so, was just having you in the lab and having you be a friend and a colleague in the space, which we all miss right now. But it's been an absolute pleasure. We'd love to see you present your work here, and congratulations again. So thank you.
Thank you so much. I appreciate your words, and I was really happy to present my work to all you.
Thanks, Esen. It was great.
Thank you.
Yeah. And so everyone, so that concludes the first student seminar. And so I just want to thank everybody. And we'll close with a little goodbye from Jack here. But just so everyone knows, we are going to post this recording once we get it annotated and captioned. It will be available for everyone to see. And again, thank you to Leidos for being a big partner and a big sponsor to allow us to do this and to drive a lot of the work in the lab. And we'll close with just a goodbye from Jack.
Yeah, let me just thank everyone who's helped put this together, and especially thank Esen and all of the other candidates who were nominated. And I think we have, going into the future, lots of future great talks like this one. And so I just hope everyone has a great holiday and do well in your finals if you're taking finals. I can't really see who's actually on the call, but we have a good number. Please, kind of, given it's an inaugural one, please talk to your lab mates and others, and that they should also in the future be involved and nominate and also get and listen to the lectures. I think they're very, very helpful. It's really excellent to see the kind of collaboration that's going on and the work that crosses different domains. For example, a lot of what Esen presented comes out of computer science, for example, and it also comes out of mechanical engineering and so on. So I think it's a fabulous example of CPS work.
Absolutely. Thanks, Jack. And so a big thank you to Jennifer Berman and to Eric Newsom, the two staff that helped set all this up and run today. And again, thank you everybody for attending. If you have questions, please feel free to reach out to me or Esen, and we can get those answered for you about the project. And otherwise, we hope to see you around and have a great end to the semester. Thank you.
Thank you. Have a good day.
All right, bye.